Now we're going to be looking at the next little section here to do with the motor effect, and that is to do with forces in parallel wires. So we have just considered the motor effect. That is that when a charge, and when that charge moves through a magnetic field, specifically in a conductor, that conductor experiences a force, and we called that force the motor effect, and we were able to predict the direction in which it could go due to our right-hand palm rule. And then we learned more about the motor effect in terms of its equation, how we can calculate it, and the variables within it. Now we're going to be looking at a conductor, but this time conductors that are parallel. And we're going to do this qualitatively first. We're going to be able to predict and explain why wires are attracted or repelled from each other. And then we're going to look at a quantitative investigation you can do in the lab. And then we're going to look at the formula that's on the formula sheet and a variety of ways in which they can test you on that. So it's all linked together. We're building up the blocks of your understanding. Have you noticed that when I've been doing these videos, I've been doing a technique for study that you guys should be doing, which is called active recall. I've been going back and I've been recalling the information that you've done in past videos, and that's what you should be doing every time you study, is linking back to what you previously had done to see how much you can remember. You're actively retrieving the information. If you can't remember it, of course you look at your notes and you add that information in there. Important study tip. So let's have a look at what we're looking at here in this video. So here are the dot points again from the syllabus that we've seen before. Conduct a quantitative investigation to demonstrate the interaction between two parallel current conducting wires, right? That's what we're going to be doing, or current carrying wires, I should say. And then this is the formula that we're going to be looking at in a little while, right, in a couple of videos time, but I've got it here because it's sort of connected together in the same section. So we're going to be dissecting this dot point out. And even though it says conduct a quantitative investigation, well, we want to start off with qualitative first, because even though it doesn't explicitly say it here, they do test this quite a lot in the course with multiple choice questions, with more longer response questions. So we really got to talk about it and explain what's going on from a qualitative perspective before we delve in and actually start doing some numbers. So we're going to be doing that in this video here and the next two videos. So let's get into it. Alright, so if we just recall some information what we've previously seen, we've seen our right hand grip rule before, where we can direct the thumb in the direction of the conventional current and the fingers wrap around the wire, and that allowed us to predict the direction in which the field that is created around the wire as a result of the movement of this positive charge. Now if I look at this, I can draw a line from the wire to the first region or potential. Remember, this is actually just a potential field, right? Remember back in year 11 we talked about equipotential lines. They are the lines within a field that have the same potential. Well, here is our first little potential line here, and if we were to measure the magnetic strength at that point, we would have a certain value. If we were to go further out, then I have my next sort of region, I guess you could say, and we could have a magnetic field value there. And so we can have a relationship between the distance away from the wire and the strength of the field, which we've talked about before. We've said that as you move further away from a magnet, the magnetic field strength decreases. And in year 11 we looked at this equation here, which we're going to build on now in this little section of videos that we're going to be doing. It says the strength of the magnetic field is dependent upon this section here, right, which is really just a constant. It's the magnetic permeability of space, and 2 pi. Okay, in fact it's 2 pi r. And what's 2 pi r? 2 pi r is of course the circumference, which is the circumference of this circle here, right? And we know that as the radius gets larger, so as we go from r to 2r, then the circumference is getting larger. As the circumference is getting larger, then the field is getting weaker. And we can see this in this relationship here, where we have the field strength here and the distance r. And this graph should look familiar to your eyes because it's an inverse proportional graph. Okay, so these concepts are just revising from year 11, but I'm bringing them to your mind now because we've got to make sure we understand all of this, because we're going to be building on this equation soon to make the equation that you see on the data sheet for the force between parallel wires. We should understand that it's an inverse relationship, because we're going to get questions in the HSC where they say if you have two wires and you move them further apart, what is the effect of the force? Well, you know it's an inverse relationship there, so as R increases, the magnitude of the force between them should decrease. And so I'm bringing this information back to your brain from year 11, because we're going to build on that now. Okay, so let's have a look at our wires now. So if we have one wire that's going up the page like this, it says current 1 is going up. So I want you to get your right hand right now and prove to you and me and the picture here that this is the correct description of the field. So we put our thumb going up, we curl our fingers in the direction of the field, which is saying that, see with this diagram, it's saying that the fingers curl around this way, and therefore the field goes around that way. So when the field is coming out towards you out of the page, it's a dot, and when it's going into the page, it is a cross. Remember, that is the convention that we've been using. And so we can represent the field around this wire as I've done on this page here. Notice that the distance between the dots are closer when they're closer to when they're nearer the wire, and then now they're further apart as I move away from the wire. Remember, I'm trying to show a graphical representation here that the field is getting weaker as you move further away from the wire. Okay, so if I get a second wire and place this second wire in here, and it also has a current, I2, going in this direction, what is the force that's experienced by that wire? So what force is experienced by wire 2 due to the fact that it is within a field from wire 1? Okay, so I'm being very careful in how I use my terminology here. So if I have wire 1, it's already got the field, we've just drawn it out. If I place a second wire here now with a current going through it, what force does it experience? Well, remember, in this whole section we've been talking about that a current moving through a field will experience a force, won't it? And that force is the motor effect. Okay, so if I have my little positive charges here moving in this direction, and it's inside a magnetic field, as you can see here, I've got my crosses. Let's use our right hand palm rule now. We put our fingers into the page, right? Yours will be going into the screen. We're going into the screen, your thumb goes in the direction of the field, which is going upwards, which means the force that's coming out should be going this way towards the left. So this wire will experience a force going towards the left due to the field that it is in, right? Very important, this field is not the field generated by this wire. This field is the field generated by this wire, which causes a force to act on this wire here, and that force is going inwards. Okay, so we've just shown that when you have two wires in which the current is parallel, right, and I'm not sticking my fingers up at you, I'm just saying they're going parallel. So when two wires have current going up in the same direction, that we have this attractive force where this wire will be moved towards wire 1. Well, what about if we look at the force now from the other side of the coin? Let's now think, okay, here's my wire for wire 2. If I use my right hand grip rule now, and I put my thumb into that direction, my fingers will curl around, which means that the field from this wire 2 means that it's coming out of the page like that and into the page on the other side. So the field from wire 2 now, if we're focusing on that, comes out of the page, right? I'm pointing to the screen, which you can't see, but it comes out of the page and then into the page on this side. So if we now think, okay, here's my wire, wire 1. What force does it feel due to the influence of the other field from wire 2? Well, let's have a look. Current is going up this way, okay. Here is the field from this wire, right, the dots, right, just ignore the crosses at the moment. We're just looking at the dots here because it's the dots that represent the field from wire 2. So let's get our thumb up for wire 1. We get our fingers, okay. We put them in the direction of the field, which is actually the dots, so it's got to come back towards you, right, from the screen. We put our thumb in the direction of the current for wire 1, and that your hand should show you that the force is going inwards. So what have we just done there? Well, we have used our understanding that around each wire we have fields. Those fields cause a force on the other wire, and we've just shown when we've looked at each individual wire that the force is going inwards. And so overall, parallel wires with current in the same direction attract each other. Okay, and we can prove this in the lab with some experiments, and make sure you watch those videos on those lab experiments, which I'll put below this one here, right? But you can see here that the overall concept that you guys have to remember is parallel wires with current in the same direction cause an attraction of those wires. And we can explain it qualitatively in terms of our right hand palm rule and our right hand grip rule when it comes to fields. Okay, so that's one way. We could also explain it, if we wanted to, in terms of fields and our understanding of the law of superposition. Okay, so this is another way in which we can describe the movement or the attraction of these wires. So remember, back in year 11, we looked at the concept of superposition, right? And we did this in terms of waves, if you remember. I'll just draw it here. Remember we said the waves can go like this. And if I have a second wave, let's do a different color, a second wave, and that second wave was in phase with the first wave. So at each point, here's a crest, crest, coming down the crest, trough, trough. At every single point in both of those waves, they are in phase. Now when that happens, we add them together. So remember, the law of superposition is we add the vectors together. And that means that the resultant wave would be higher and have a greater amplitude, like this. Same frequency, but greater amplitude. And so that was constructive interference, right? Then if we have two waves that are out of phase, we had destructive interference. And that was called the law of superposition. Now that law of superposition can also happen with fields as well as waves. And so let's have a look at our fields here. So if we have our two wires both going in the same direction, let's get the laser, there it is. Okay, so the field around both of these wires is anti-clockwise. So here it is, going anti-clockwise, going around that direction at every point, anti-clockwise, right? So that means in this middle section, this wave, and I'm going to draw this now, and I'll draw it in green, this wave is coming this way. It's coming towards us, coming out of the page. Well, from the other wire, wire 1, the wave is going in the opposite direction. So if they're going in opposite directions, that means they're going to cancel each other out, aren't they? They're going to undergo destructive interference. So if they're going destructive interference, that means that we're going to have a region of weak field, and on either side they're going to be stronger field, and those wires will come together. Let's have a look at another way in which we can draw this and represent this. And this is looking from the wires from the top, right? So for my eyeball was up here, and I was looking down, I would see the current coming towards my eye, right? So there it is with the little dots representing the currents coming towards my eye. And we use our right hand grip rule. We put the thumb that's coming out of the page, our fingers curl around in an anti-clockwise direction. So there it is, it's going anti-clockwise. Alright, now what that means is that the field here is going up on this side and the field's going down on this side. So they're going in opposite directions, which means we have destructive interference in the middle, which means we have a weak field in the middle. So therefore the wires are pushed towards each other. So we get the same overall end result. Parallel wires with current going in the same direction attract. And we can explain that in two different ways. We can either explain it in terms of our right hand palm rule and our right hand grip rule, or we can explain it in terms of fields, in terms of interference, destructive and constructive interference. So there's two ways in which we can do that. So that's it for this video. I've got a lot of material in this video. Make sure you take notes. Make sure you revise the concepts, because I'm bringing back some Year 11 concepts there, but we're going to build on those and use those for our Year 12 knowledge. So that's it for this video. Keep studying. Remember always, if you think that these videos are very informative and you're getting a lot out of them, make sure you go see the study bite sessions and of course the questions, because there's lots of questions that you need to do. Watch the video answers on those, and if you like it, share it with your friends in terms of that they purchase the courses. Okay, don't share the password, same as I always say. Okay, for the price of a movie ticket you get access to all of this video answers and insight into the study cards, etc. It helps me make more of these for you. Okay, it costs me a lot of money for everything that I do in terms of the website, in terms of the graphics, in terms of, you know, the videos and the equipment that I use. So please be authentic to that. For the price of a movie ticket, you're supporting me, and get your friends to join, and together we can get you over and get you a band 6 in your HSC. See you next video. Alright, before we go to the next video, I want you to check out more courses that we have here on our YouTube channel, which are just small snippets from the actual bigger courses that we have on theflipteacher.com. Of course, with all of our courses, we try to incorporate practical sessions. We have study cards, we have posters that you can print off and stick around your room and do a lot more. We have up to 68 or more videos per course. That's like 9 to 10 hours of material that really delve deep into the syllabus and looking at essential content, skills, mathematical manipulations, and a lot more. So if you like that, go over to theflipteacher.com and check it all out, and I'll see you in the videos.